Hello everybody. It is finally time to see if we can consider a functional of the density as the unique functional of our quantum mechanical observation. It is indeed possible to demonstrate that every observable in the ground state is a unique functional of the electron density. If we have the electron density, we have in principle one and only one value for our observables, so for our measurements. This is the main outcome of the Hohenberger-Kohn theorem. It is mainly due to Walter Kohn, an Austrian and American physicist, here he is, who developed the density functional formalism in the early 60s during his sabbatical in Paris. The concept of functional of the density is not new, and was not even new, of course, in the 60s. As we mentioned in the historical part later this week, ideas about expressing concept and observables in terms of the density were already there. Walter Kohn, however, formalized this framework and gave very solid mathematical foundation to this approach. In this and the following modules, we are going to see together this foundation. Let's start then from what we already know. We could, for instance, say that every observable is a functional of the many-body wave function. If we know the wave function of a system, we know how to evaluate observables via the expectation value. The psi represents the system. However, if you know psi, we already solved the problem, right? Now the question is, what does represent the system? In mathematical terms, we can ask, what is the ingredient of the Hamiltonian that describes the system, that distinguishes a system from another? If we have a non-relativistic Hamiltonian of a many electron system in the Born-Oppenheimer approximation, the ingredients are the kinetic term that acts on each electron, the electron-electron interaction given by the Coulomb potential that acts on each couple of electrons, and the external potential, for example, given by the potential of the nuclei that again acts on each single electron. So, in this case, what is the ingredient that defines the system? Clearly, it can't be the kinetic or the electron-electron term. They are in fact universal. They do not depend on the system. No matter the situation, the kinetic operator will act as a Laplacian, and the electrons will interact in couples via a term that is inversely proportional to their distance. Just to give you an example, we can consider an atom of nickel. It contains 28 electrons. And bulk silicon, again, 28 electrons in the unit cell. They are clearly two completely different systems. And the difference lies in the position and the strength of the nuclei potential, here taken care by the external potential. So the external potential is the quantity, the ingredient that defines a system. In fact, if we have the external potential, we automatically have the Hamiltonian. And if we have the Hamiltonian, we are in principle able to diagonalize it and obtain eigenvectors, the wave function, and eigenvalues, the energies of the system. We can then evaluate any other observable via the expectation value of an operator, taken with the wave function. For example, here, the electron density, that is the expectation value of the density operator. So, if the expectation value of an operator depends on the wave function, here we consider the ground state wave function, which in turn depends on the Hamiltonian, and hence the external potential, can we say that each observable is uniquely determined by the external potential? In other words, can we say that each observable is a unique functional of the external potential? This is a crucial point for our DFT course. So I invite you to think a moment about this question. Let's see. In order for the observable to be uniquely described by the potential, since it is uniquely described by the many-body wave function, we need the external potential to be in strict relation with the wave function. In particular, we need the one-to-one correspondence. We call this a bijection. If we have two different potentials, we should have two different wave functions, so giving us two different measures for an observable. And vice versa. Two different wave functions come from two different potentials. Okay? But is this the case? Well, let's see what we can immediately say about this mapping. For a given external potential, we can diagonalize the Hamiltonian and obtain a wave function. We can change the external potential, diagonalize again, and obtain a wave function. Another one, or the same as before? We cannot say, but certainly we obtain one and only one ground state wave function. So we can at least say that this mapping is a function, because it is a surjection. What we are excluding here is the situation in which you diagonalize a given Hamiltonian and obtain two ground state wave functions. Clearly not possible. Or is it? Let's think about it. Yes, there is still the possibility to obtain a degenerate ground state, so more than one wave function. Like here, two psi's belong to the same ground state energy. And actually, every linear combination of the two psi's will still be a wave function of the same Hamiltonian associated to the ground state energy. Now, for simplicity, we will not speak too much about degenerate ground states, but take into account that the generalizations are possible. After all, you can always consider a mapping between an external potential and the set of all wave functions abiding to the same ground state energy, like here. But these are nonetheless subtleties, and for more details, I suggest to have a look at this reference if you want to know more about degenerate ground states. Let's get to the original mapping then. We know that this is a function. So, first question, is it an injective function? Because if it is, that would mean a one-to-one correspondence between the external potential and the wave function. And so it would also mean that any observable is a unique functional of the external potential. And second question, can we go a bit further and consider the very same mapping with the density? The answer to these questions constitute the Hohenberg-Econes theorem. We are going to demonstrate this in the next video. Do not miss it. Goodbye.